Well, I'm not sure how many of you have been here in the Simon Center before, but in any case, I welcome again those who came before, and I also welcome those who come here for the first time. These type of lectures are offered by the De La Pietra families, which is a set of benefactors who enjoyed not only to give us the possibility of bringing excellent scientists, but they always insist that one of the lectures should be given to high school students as an inspiration, because at the end of the day, you are going to be the ones coming after me and after him and after all the people in this place, and perhaps some of you will also be scientists working in Stony Brook or somewhere else. So today we're bringing you someone from afar. Professor Fumiharu Kato is from Japan, and he's going to give you an incredible trip through number theory. If you thought that you know about natural numbers, negative numbers, rationals, and how do you go from rationals to the reals, wait, because you are going to get plenty of surprises. So please, Fumiharu.
So thank you. So thank you for the introduction. And so my name is Fumiharu Kato. I came from Japan 3 weeks ago. And so sometimes my English stops because my English is a little is not so good. So, but I try to do it, and I will do my best. So today I'm going to talk about a sort of a very special and extraordinary sort of numbers. So it's something like never-ending. So it is infinitely many something. So so let us go into this extraordinary and fantastic world of numbers. So, but let me start from a small quiz for you. So I challenge you by this quiz. So 25 squared is 625, whose last two digits are the same as the original number. So you have 25 here. So this gives you back the 25 you started from. So the question is, find all such two-digit numbers that have this same property. Okay, this is the question. So here, there is a small remark. By saying two-digit number, I also mean one-digit number. So I prepend 0 to one-digit number to make it two digits. Okay? So 0 and 1, for example, are regarded as two-digit number in this quiz. So we already know 0 is, 0 squared is 0. That means 0, 0 squared is 0, 0. So this is certainly a solution. And 0, 1 also, 0, 1 squared is 0, 1. So this is also a solution. And 25 is also a solution. So we have three solutions, right? And the question is, do we have another such number or not? So who thinks there's other numbers? Okay. And who think otherwise? Okay. So maybe this two-digit version of the quiz is a little too difficult to attack for the first time. So I give you a hint, the little more toy sort of model. So this is a one-digit one-digit version. So it is certainly a much easier one. Okay. So 5 squared is 25. I'm sorry. 6 squared? You mean the solution for the one-digit? Yes, you're right. Yes. 6 actually is one of the solutions. 5 squared is 25, but I just go on, right? So whose last digit is the same as the original number. So find all one-digit numbers that have this property. And this is, of course, much easier than the original question. So what you do is just list up all the possible number, one-digit number, from 0 to 9, and you square them. Then, looking at this table, then you find that there are only 4 such numbers. Okay? So you have answer that is given by 4 numbers, 0, 1, 5, and 6. Okay, that's the one-digit case. So let us go back to the two-digit version. So what will be the solution? So we already know, as I have told you, 0 and 1 and 25 are the solutions, And any others? Okay.
The squares are the same numbers as before.
The square should.
So like 0 squared is still 0.
Yep.
1 squared is still 1.
Yeah, but 25 is not, 25 squared is not 25.
The 5 squared is 25 and then 25 works.
25 works, yes, because I only look at the last two digits. Okay? Yeah, that's the point of this quiz. So 25 squared is not 25, but 25 squared has 25 in the last digit. Okay, that's the point. Okay? And do you have any other such? Oh, okay? Yeah, please think. I give you, okay. Sorry? 36. So you are you sure that 36 squared has 36 at the at the end? Okay. So any other opinion? So okay, please. Sorry?
50.
30.
Oh, 50.
50. Huh? Are you sure? Okay. So if not, I give you one more possible number, 76. 76 squared is 5,776. So this gives you back two digits. That coincides with the 76 we started from. And any other? And actually, there's no other. So there are only 4 such numbers. So there are, okay, there are only 4 such numbers. So the solution is given by 0, 1, 25, and 76. Okay? So I give you how to find these 4 numbers and how to find that these 4 numbers are the only possible solutions. First, we have to observe that the last digit of the solutions of the 2-digit version should be solutions of the 1-digit version. Like, for example, 25 is a solution of the 2-digit version, and it has 5 at the last digit, which was one of the solutions in 1-digit version. And this should apply to another possible solutions of the 2-digit version. Okay, this point you should first observe. Okay. Then we know that the solution should be of the form 10x plus 0, 10x plus 1, 10x plus 5, or 10x plus 6, where x is the second digit. And the requirement is that these numbers should, these numbers squared have the same last 2 digits. Okay. So the requirement written in the formula is the following. So I square this number. For example, if I take 10x plus 6 from this list of 4 possible cases, so 10x plus 6 squared should have 2 digits, to the last 2 digits, same as the original number. That means that if you subtract the original number, this number should end up with 2 zeros at the end of the digit of the decimal expression. So that means that this number should be divisible by 100. Okay? And you transform this to appropriate expression like this, then the first term is obviously already divisible by 100. So the remaining term, 10 times something, this should be divisible by 100. And that is to say, x plus 3 here should be divisible by 10, but x is a digit number, so this has to be from 0 to 9. So there's only one possibility for x to satisfy the property that x plus 3 is divisible by 10. That means x should be 7. And that means that the number we seek is 76 and no other. Okay? And we do the same for the other possibilities. I mean, 10x plus 0, 10x plus 1, and so on. And we see that there is only one possible value of x in each case, so that we know that there are only 4 solutions also in the 2-digit case. So that's the the procedure you do for have to obtain the solutions. So now we go on to the 3-digit version. So how many numbers should be the solutions? Find all 3-digit numbers with the property that the last 3 digits of its square are equal to the original number. Okay. Then I think many of you have imagined that there are only 4 of them. So 0, 1, and actually 625, and the other one is 776. I'm sorry, 376. And the square is this number. This certainly gives you back the original number at the end of decimal places. I mean, the last 3 digits gives you back the original number. Okay. So the answer is 0, 1, 625, and 376. And in order to get this, you do approximately the same as before. So first observe that the last 2 digits of the solution of the 3-digit version are the solution of the 2-digit version. Okay. And so we know that the solution for the 3-digit version should be of the form I mean, there are 4 such possibilities. So 100x plus 0, 100x plus 1, 100x plus 25, 100x plus 76, because we already know that these are the solutions. I mean, 0, 1, 25, and 76 are the solutions in the 2-digit version. Okay, and next we do is square them. For example, if I take this last possibility, then we square it and subtract the original one. Then this one should end up with 3 zeros in decimal expression. So that means that this number should be divisible by 1000. And this left-hand side is transformed in this way. A little bit complicated, but not so difficult transformation of the formula. Then this first term is already divisible by 1000. So we know that this remaining term should be divisible by 1000. That means x plus 7 should be divisible by 10, where x is a digit number. That means x should be from 0 to 9. So there's only one possible x. That is, x is 3 is the only solution. And that means that the number we seek is 376. And we do the same for other possibilities. And we see similarly that there is only one possible value of x in each case. So we have only 4 possible solutions. So this is 3-digit version and 4-digit version. So let us see. Is like this. Okay, so 625 used to be is a solution of the 3-digit version, but it is at the same time it is a solution for the 4-digit version, because the 600 squared is something end up with 0625. Okay, so it gives at the same time is a solution for the 4-digit version, and another one is 9,376. So we have this answer. So what about 5-digit version? Is this? Okay, like this. So you go on like this, and 6-digit, 7-digit, 8-digit, you go on. So in general, so now comes a general sort of fact I can present you. So there is a theorem. I mean, I just box it like as a theorem. So for every n is equal to 1, 2, 3, and so on, there are always exactly 4 such numbers, 4 numbers with at most n digit in decimal expression, whose square has the last n digits equal to the original number. There's only 4. such numbers, and there are actually 4 such numbers. That is, so in other words, if I put in another way, if, for example, A is a solution of the n-digit version where n is a natural number, then there exists one and actually only one possible n plus 1th digit x, where x is from 0 to 9, such that the number you append x in front of A, so it is this number, 10 to the power n x times a, x plus a, is a solution of the n plus 1 digit version. So you prepend only one possible next digit, and next digit exists, and only one such digit exists. And you go on like this. Okay? And so we know that, so we have 4 such solutions always, and 2 of them are just 0 and 1. And the other 2 are of the form something like this, end up with 5, and something like this, which ends in 6. So you have this form 4 numbers. So I give you a small animation. So 76 square is like this. So a 3-digit version, 4, 5, 6, 7. So you have this still. You can go on. You can go on, and you have a, you see. I mean, this is already a very, very big number. So square of this is, of course, it's much larger number, but it gives you back the original number at the end of the decimal places. This here, and I can go on up to 14th digit. This is the 14th digit actually. Okay. And I can also show you my calculation. So 48th digit. So this. So you have 4 such number. It goes on infinitely many times. So you have 0 on the at the bottom, and you have 1 with many, many zeros prepended, and some number starting from 5, and some other number starting from 6, like this. So you somehow goes on to infinitely many times to a prepend number in only one way to get the solution of the n-digit number of the quiz we started from at the beginning of this lecture. So and it goes on and on like this. Okay, so before getting into another aspect of my story, I would like to give you a small sort of explanation, I mean the light explanation, how this theorem should be proven. And you will see that the method of proof actually repeats what we have already done in the particular case where n is 2 or 3 at the beginning of this lecture. So let A be one of the solutions of the n-digit version. Okay, so A is a number from 0 to 10 to the power n minus 1. So this is a number at most n-digit in decimal representation. So our assumption is that a square minus a should be divisible by 10 to the power n. That means the a square, I mean the last n digit, am I correct? So last n digit of a square repeats repeats a, the original you start from. So a square minus a can be written as 10 to the power n times something, where b is a natural number. Okay? And suppose 10 to the power n times x plus a is a solution of the n plus 1 digit version of the quiz. Okay? Then, as we have already done, we consider this expression. This number squared minus itself. okay? And this has to be divisible, this time has divisible by 10 to the power n plus 1. And we transform this in appropriate way, we will find that this formula in the bracket should be divisible by 10. So this is what we obtain from this transformation of formula. So it's not so difficult to do. Okay, and we go on. So the nth digit of x, nth digit x is characterized by this formula. I think you already know this formula. I mean, this here is a bar, and you know what it means. So bar, here's bar means the right-hand side is divisible by the left-hand side. Okay? Or equivalently, 10 divides 2 times a0 minus 1 times x plus b, where a0 is the last digit of a. So because we are only looking at the divisibility by 10, so we can just throw away some term which is already divisible by 10. And a0 is the last digit. Okay, all the rest is, already divisible by 10, so we don't have to think about them. Okay, so we just look at the last digit. Okay. Now, 2 times a0 minus 1 is minus 1, 1, 9, or 11. If, here, a should be a0. So this is typo. If a0 is 0, 1, 5, 6, respectively. So we know that there are only 4 possibilities in one-digit version. So if a0 is 0, then 2a0 minus 1 is minus 1, and so on and so on. Okay? So this part we know. Hence, x is characterized by either this or that. So x minus b is divisible by 10 when a0 is 0 or 5, or x plus b is divisible by 10 when a0 is equal to 1 or 6. Okay? So if this is the case, then x should be equal to the last digit of b. Okay? And if this is the case, x should be equal to the, so to speak, the complement mod 10 of b, of the last digit of b. So in any case, x is uniquely determined by this property. And that's the proof. So you have n digit, then there's only one, and there is such a possible next digit, and there's only one choice. And that means that you have only one way to extend your solutions to the next digit version. Okay, this is a proof. So now I think is more or less the half of my lecture. So let's go on. So there is a generalization of this theorem, and I will come back to this theorem at the end of my talk. So this theorem says the following. So let m be a natural number greater than or equal to 2. And this used to be, in the beginning of my talk, this m used to be just 10. So this should be a base of our p-adic expression of a number. And f bracket x is a polynomial with integer coefficients, where the degree of the polynomial k can be just arbitrary. Okay. In our quiz, in the case of our quiz, this polynomial used to be x squared minus x. But this polynomial can be just general like this. But the requirement is that the coefficients should be integers. So then let a0 be an integer such that 0, it is non-negative and at most n minus 1. So that is to say a0 is the first digit, is a digit number of p-adic representation. And the second requirement is that if a0, if you substitute a0 into f, then the result should be divisible by m. And the next one is a little bit weird looking. F prime is a derivative. I hope you know what derivative means. Differentiation. So if you plug in A0 into the derivative of f, then the result is co-prime to m. This is a third requirement in the theorem, the assumptions. Okay. Then, so for any integer n greater than or equal to 0, there exists uniquely an integer a sub n such that these three properties are satisfied. So one is an is non-negative and is at most m to the power n plus 1 minus 1. That is to say, an is represented by an Emery number of at most n plus 1 digit. Okay? And the second property it has is that m divides an minus a0. That means that the first digit of an in p-adic representation coincides with a0. Last digit or first digit. I mean, so maybe the last digit is the proper way of speaking. And the third one is the most important property. Actually, f plugged in, an plugged into f is divisible by this high power of m. So m to the power of n plus 1. That means that this thing, if you expand if you expand this number in p-adic representation, you have zeros, n plus 1 zeros. Okay. So this is a theorem which generalized the theorem before we have treated before, and so I'm going to get back to this theorem at the end. But in order to get into a more detailed and more sort of interesting sort of, the aspect of this world, let me then start another sort of story. This is about the p-adic expansion. I think many of you have already learned about p-adic expansions of numbers, and I would like to just recall the concept and also how to obtain p-adic expression. So, so here's the theorem. So let us fix a natural number m at least 2. Then every natural number m can be expanded in Emery or p-adic expansion. So here's some examples. So I take this number 1234 as just an arbitrary example, just chosen randomly, and I'm going to expand in Emery for several m's. So let me first start from m is equal to 10. Then this gives you back just 1, 2, 3, 4. Just as we see, because we usually display number in decimal expression. But that means that this number can be decomposed into this formula. The 4, starting from 4 is the last digit. 4 plus 3 times 10 plus 2 times 100 plus 1 times 1000. And that gives you back the decimal expression of 1, 2, 3, 4. Yeah, so you pick up these number to the opposite direction, and this gives you this. And if you, for example, choose m to be 7, then you can have a 7-adic representation of this number, and you will find that this number is 2 plus 1 times 7 plus 4 times 7 squared plus 3 times 7 cubed. And that means that in 7-adic representation, this number can be represented as 3, 4, 1, 2. And I write 7 here in order to emphasize this is a 7-adic expression. Okay? And if I go on, for example, m is equal to 5, then this number can be represented in this form with 5 digits. So this means that 4 plus 1 times 5 plus 4 times 5 squared plus 4 times 5 cubed plus 1 times 4th power of 5. Okay, so I think many of you already know this. And how to obtain this, you also know. Let us find the m-adic expansion of some number n. Okay, so let a0 be the remainder when n is divided by m. So this is the last digit, so to speak, of the m-adic expression we seek. So for example, if n is 1, 2, 3, 4, and m is 10, then we take a0 to be 4, because we take the remainder divided by 10. Okay? And before getting to the second step, we take the quotient of the division. B0 is the quotient of that division we have performed. That means that B0 is equal to n minus A0 divided by m. In our example, if n is 1, 2, 3, 4, then B1 is 1, 2, 3, 4 minus 4 divided by 10, so it's 1, 2, 3. Okay? 123. Next, let A1, the next digit, A1 be the remainder when B1 is divided by m. Okay, you go on like this. B1 is 1, 2, 3. So you take the remainder divided by 10. So A1 is 3. Yeah? So then you take the B2 to be the quotient of this division. So in our example, B1 is 1, 2, 3. So B2 is 12. Okay? And you go on. So A2, the next digit, is a remainder when B2 is divided by m. So B2 is 12, so A2 has to be 2. And B3 is a quotient of that division. So B2 was 12, so B3 should be 1. Okay, so then you go on, let A3 be the remainder when B3 is divided by n. So B3 was 1, so A3 is 1. So repeat the above and stop the process when bk plus 1 at some k is 0 for some k non-negative. So in our case, before, it's going to be 0. So we stop here. Okay, then we obtained numbers. A0 was 4, and A1, 3, A2, 2, and A3 is 1. And we order these numbers in opposite way, 1, 2, 3, 4. That gives you the decimal expression. And you do the same for general m. So you you start from AK where you had 0, B0 is 0, BK is 0. So, and you order these numbers in opposite way. And this gives you back the MRE representation of the number. So very, very simple process. But here, there is a very important number theoretic aspect in this construction, actually. So what is important here is that this process actually ends at some point. So you have to have at some point you have to have 0, which stops this process. And this has to be proven. This is a non-trivial sort of a theorem in mathematics. So the above procedure will eventually end. In fact, if m to the power k minus 1 is less than or equal to n, and n is smaller than m to the power k, then n has the k-digit m-adic expansion. So you repeat that process k times, then eventually you get 0, bk is 0. So this means that you have to stop there. Yep. However, this is only true if n is positive integer. So because n is a positive integer, this procedure actually stops at some point. Indeed, if n is negative, if you do the same, if n is negative, so have you ever tried? If n is negative, and you do the same process to get the MRE expression, then the above procedure never stops. Okay, I'm going to do it for n is minus 1. Okay. So as a trial, let us try the procedure with n is -1 and m is 10. So decimal expression of -1, so to speak. So the first digit should be 9 because this is the remainder when n is -1 is divided by 10. So the remainder is 9. And the quotient is -1 because it is -1 minus 9 divided by 10. So it's -1. Okay. Then next, A1 is again 9 because it is a remainder when -1 is divided by 10. And we take the quotient, next step, which is again -1 because it is -1 minus 9 divided by 10. And you do the same for A2 is 9. The remainder, which is a remainder when B2 is -1 is divided by 10. And B2, I'm sorry, so here is B3. I'm sorry, B3 should also be -1. You go on like this, just forever. So this goes on forever. So that means that you have this kind of decimal expression of -1. So let us take this positively. Let us interpret what was happening in this process. I mean, we know that now the process doesn't stop, and it just go on forever. But maybe this would mean that -1 has a decimal expression like this. -1 is equal to some number expressed by infinitely many 9s. I mean, infinitely many, with 9. I mean, the first digit 9, the second digit 9, third digit 9, and so on and so on. Okay. The important thing here is that even if we use this kind of infinite digit decimal expansion, which maybe, I mean, you would think it is absurd, we can perform calculations just like ordinary numbers, actually. So I'm going to do some of the ordinary calculation using this number. And maybe you will be surprised. For example, calculation with infinite digit number like this, calculation 1. So if it is -1, then adding 1 gives you 0. And indeed, it gives you 0. Okay? If I add 1 here, then 1 plus 9 is 10. So you have carry 1 here, and 1 plus 9 is 10. You carry 1 here, the 1 plus 9 is 10, and so on and so on. That gives you 0. Okay? So I mean, this. I mean, you have infinitely many zeros, but it is 0. Okay. So next one, the calculation that's number 2 when squared. So -1 squared is 1. So let us do it. Is this? Okay. So here's -1 and here's -1. We multiply them. Okay. 9. Times 9 is 81. So you have 1 here and carry. As a carry, you have 8. And 9 times 9 is 81 plus the carry. That's 89. So 9 here and 8 as a carry to the next digit. So 9 times 9 is 81 plus 8 is 89. So 9 comes down. And you have the carry 8. Again, and again. So this goes on like this. So you have this number and that number. I mean, the same number. Infinitely many times you write this downstairs, and you try to add them. But addition is actually possible because here, for example, the first digit you only have 1, and the second digit you only have 2 of them. So you can just take a summation of 9 and 1. Is 10, so here is 0, and the carry is 1. So the next digit, 9 plus 9 plus 1 plus the carry 1. So this is 20. So you have 0 here. The carry is 2 in the next digit. So 9 plus, then what's going on? So 9 plus 9 plus 9 plus 1 plus 2. This is 30. So you have 0 here, and the carry is 3, and so on and so on. So you have actually 1. As a result of the calculation. Yep, do you believe it? But this is it. So the third one is a little more sophisticated one. Okay, calculation number 3. The formula for the sum of an infinite geometric series. I think many of you know already what it is. So this is a kind of a formula, infinite to many terms. 1 plus r squared plus r cubed plus and so on and so on. This converges to this rational expression of number when the absolute value of r is at most, is less than 1. In this situation, I mean, if r is small enough, then this infinite series converges into this number. This was what we have learned as the formula for the sum of an infinite geometric series. Okay? And I'm going to plug in r is equal to 10. So let me do it just. Then 1 plus 10 squared plus and so on and so on. So this, I mean, we find that this is exactly the decimal expression, infinite to many digits, consisting of infinite to many ones. Correct? Yeah? And if I believe this one, then this is equal to minus 1 over 9. Okay? Then I multiply both sides by 9. Then this gives you back this decimal expression of minus 1. Okay? Of course, I mean, plugging r is equal to 10 is something you cannot do in the ordinary situation. But we just formally, I did it, okay? Yeah, so now I have shown 3 evidences why this expression of number, minus 1, in decimal places is correct, so to speak. It is correct to some extent. I mean, it's not correct in real number sort of world. Maybe it is correct in another world of numbers. And also in this another world of number, you can just carry out the usual calculation. And if you can do that, then maybe, I mean, then why don't you, I mean, just regard these numbers as a number? This is what am I going to suggest today in today's lecture. Okay, so here was the third sort of thing. So now let us come to the nature about the numbers of infinite digits. Okay, even if the numbers have infinite digits, one can still compute consistently with them. I mean, whole consistently. In other words, they function as numbers. The problem here is that they are perceived as absurdly large numbers. That is to say, they are incompatible with the notion of magnitude of numbers. But maybe you can just throw away this concept of magnitude. Maybe this number doesn't have any magnitude, but just a number, just a sort of notational number, formal number. But it's a kind of a prejudice of us, I mean, from the beginning, that every number has to be magnitude, has to have a magnitude. But this number simply doesn't have magnitude. So let us think like this, okay? So however one can accept them in this way, we may think that numbers with infinite digits are reasonable numbers in many, many ways. So, for example, this number, so you remember? So this number we started from. We have started from 5 and 6 and 25 and 76 and so on and so on. So we have obtained infinitely many such numbers. And this somehow establishes a number with infinite digits. So let us put this first number to be p, and q is the other one. Okay? Then these numbers actually do not change when squared. Do you believe it? That is, they are the solutions for the quadratic equation. X squared minus x is equal to 0. Okay, let's do it. This is it. So this number, so this is q in our notation, q squared. Let us do it. So 6 times 6 is 36. So 6 is here. So 3 is carried. 7 times 6 is 42. plus carry 3 is 45. So we have 5 here, and you go on like that. And you have the second line, the third line, fourth line with arranged in this way. And finally, you have infinitely many such floors. And you sums up all the numbers, right? The first digit is, you only look at 6 here, so 6 goes down here. Okay, now you have 5 plus 2, so you have 7 here. And 2 plus 3 plus 8 is 13, so you have 3 here with carry 1, and 6, 2, 4 is 12, plus carry is 13. I'm sorry, what am I saying? So I'm sorry, it's 18. I'm sorry, is that correct? 18 plus 1 is 19. So that's why I have 9 here, and go on like this. This this is just possible. The calculation is just possible in this way, right? And you actually recover the original number here. Okay, so please abandon the prejudice about the magnitude. If you equate the kind of notion of magnitude to this number, then maybe you will not believe it. But this is just a number. Okay, so this means that these numbers are the solution, one of the solutions of this quadratic equation. Okay. Yes, and there's second evidence. In fact, we have relations between roots and coefficients, namely p plus q is equal to 1, and p times q is equal to 0. So looking at the quadratic equation x squared minus x. Okay, let us do it. So if I take a sum of p and q, then we actually have 1. So 6 plus 5 is 11. And you will find promptly that the digits are, the sum of the digits from the second digit is always 9. Okay, so 7 plus 2 is 9, 3 times 6 is 9, is 9, 9 plus 0 is 9, 0 plus 9 is 9, and so on. So once you have a carry 1 here, then the carry goes on and on, infinitely many, forever, so that you have zeros here. Okay, very good. So, and what about the multiplication? P times Q is like this. You can do the same, and you will get just 0. So this is really surprising, but this is what you get just by honest calculation. Okay, so I have shown, at least 2 evidences in order for us to accept these numbers to be just a number, which can be, for example, a solution of algebraic equation, and which also have the usual property that the solutions of the algebraic equation should have. So these are really, really nice and full-fledged and autonomous good numbers in many, many ways. Okay, but there are little problems if you go on accepting these to be a number. So I give you a few aspects of the problematic, aspects of these numbers. So up until now, we have considered infinite-digit m-adic numbers, mainly decimal numbers we have calculated, right? But in fact, in this situation, we actually have some weird things. For example, the infinite-digit decimal numbers p and q, which we have defined before, that we have discussed above, satisfy actually this weird sort of property. So p obviously is not 0. Q is not 0. But actually q times p times q was 0. We have already calculated. So here's something, 2 numbers which are not 0, but the multiplication of them is 0. So this is quite unusual sort of a situation. We have never seen in the usual number. Okay. So if we have this phenomena, then I think the most serious aspect of this is that, if, for example, you cannot consider the fraction of this. So for example, p is not 0, so maybe we can think about the fraction 1 over p, and at the same time also 1 over q. But if you multiply them, then all of a sudden you end up with 1 over 0, which is something more absurd. So which cannot be a number, which cannot be a usual number, or so the finite number. So you have a real problem if you think about fractions. If you starting from this weird sort of property. Moreover, the quadratic equation x squared minus x has 4 solutions: 0, 1, p, and q. And in schools, we have learned that quadratic equation have at most 2 solutions, right? And algebraic equation of degree 3, for example, the cubic equation has at most 3 solutions, and so on and so on. But here you have a kind of a weird phenomena that this quadratic equation has actually 4 distinct solutions, which sounds very strange. Okay, so actually this kind of a weird thing happened because 10 is not a prime number. And you will find that here we have 4 such solutions because 10 is 2 times 5. It is a product of 2 different primes. And this 2 comes up here as the number of solutions. Actually, this is a quadratic equation, so the degree 2, and you square this, 2 to the power 2, and this square, the superscript 2, comes from the number of the prime numbers that divides 10. So I think you will find by yourself if you are interested in this. But anyway, so this things happen because 10 is not a prime number. But on the other hand, if you start from a prime number, so if p is a prime number, and we consider our infinite digit numbers or p-adic numbers, then this kind of weird thing doesn't happen. And what we really get is really, really similar to the usual natural number. Okay, so p-adic numbers. Now comes more advanced and modern mathematics. So in this situation, one can consider consistently the reciprocal of a non-zero infinite digit p-adic numbers, like 1 over something, or the fractions, which is of the form like this. So you have infinite digit p-adic numbers to the left, but you have only a finitely many digits on the right of that. Okay. So you find that this is completely the other way around from the usual decimal expression of number or real number or fractional numbers. In other words, these numbers are left, right, reversed from the usual decimal representation. But they are numbers in many, many ways, as I have told you, and maybe I think I successfully persuade you that these are just numbers. So now comes a little more sort of a broad view of the numbers. So such p-adic numbers with infinite digits are considered to be on the same level as real numbers in the family of several different numbers. So we usually start from natural numbers. In mathematics, the set of natural number is denoted by this symbol, so to speak, blackboard boldface of n, which is contained in the set of integers, which is denoted by z, Zahlen in German, which is contained in q, which is the set of all rational numbers, the fractional numbers. And usually we go to the real numbers by filling in all the gaps between rational numbers by rational numbers. Okay, we know that, for example, a square root of 2 is not a rational number. So we fill in these gaps by irrational numbers to get the notion of real numbers, which is a continuum sort of numbers, which is further contained in the complex numbers. There's a complex plane, I think you know already. But you have another way of expanding numbers, actually. So from Q, you have another way to complete or fill in gaps in completely different way by using p-adic numbers, which are usually denoted by this notation. And you go on further. So you have somehow the second way, but of course, I mean, this number system differs by there are infinite many such number systems depending on the p. So Q2 and Q3 are different, Q3 and Q5 are further different. So you have infinite many such other ways to expand Q. Okay, so now comes the p-adic numbers. So what is the role, what is the important point of the p-adic numbers in modern mathematics? I'm going to explain. So my major in my math research lies in non-archimedean geometry, so to speak. And this is a geometry or analytic geometry or analysis of function theory over non-archimedean field. And non-archimedean fields, the typical example of non-archimedean fields is p-adic, actually p-adic numbers. So I, for example, I myself usually live in p-adic numbers, not real numbers. So in this sense, I mean, the p-adic numbers are somehow very, very important in many, many areas of modern mathematics. The concept of p-adic numbers is an indispensable and, in fact, very important number concept that appears everywhere in modern mathematics. In history, it was discovered by German mathematician Kurt Hensel, so this person, in the late 19th and early 20th century. So this is relatively a new number, right? So the real number has maybe first time discovered by human being, I think it is by Pythagorean groups. Maybe it is more than 2,000 years, or maybe 2,004 or 500 years ago. But p-adic numbers, this is a kind of an analog of real number, has been discovered like 120 years ago or so. So it's quite new. Since then, it has appeared in modern mathematics, not only in number theory, but also in the form of p-adic differential equations you can think about, and p-adic analytic geometry. So the thing is that real number is a continuum. And over continuum, you can do analysis. You can do, for example, the derivative, integrations, differential calculus, and so on and so on. You can also develop the differential calculus to, for example, to cook up the surfaces or more higher dimensional shapes, manifolds, and so on. So you can just develop the differential geometry based on real numbers. But you can also do approximately the same thing based on p-adic numbers. P-adic numbers are also continued in other way. So you can discuss differential equations over p-adic numbers and differential geometry, so to speak, over p-adic numbers. So you can have a p-adic analytic geometry. And actually this p-adic analytic geometry, nowadays so-called rigid geometry, this is my major. So I usually work in this field of mathematics. Okay, so here comes this person, Kurt Hensel. And let us go back to the theorem we have introduced in the middle of my lecture. So you remember this theorem. Actually, this theorem is called nowadays Hensel's lemma. So this has been first discovered by Hensel. And what we have done from the beginning as the quiz, I mean, we start from quiz, right? As a quiz is just the path. I mean, we just follow the path of Hensel in 19th century. Okay, so let us summarize what we have learned today. So calculations between ordinary numbers naturally extend to calculations of infinite m-adic numbers. However, when m is not a prime, there are various problems. For example, the product of two non-zero numbers may be 0, and also an nth order algebraic equation may have more than n solutions. That is kind of weird sort of phenomena. However, these problems do not arise for infinite p-adic numbers when p is prime. So this is really a good number. Infinite p-adic numbers, nowadays called p-adic numbers, simply called p-adic numbers, are very important in various areas in modern mathematics. That's all we have learned. So thank you very much for your attention.
Anybody has any questions or comments? Yes.
Do you have an explanation to the Casimir equation, 1 plus 2 plus 3 and so on equals -1/12 in the p-adic numbers?
Actually not. Yeah, this is really, really something else. I mean, different from what is treated in p-adic number sort of mathematics. Mm.
That has to do with analytic continuation of complex functions. Any more questions or comments? I don't see anybody. Everything was very clear. Maybe you can tell us about applications of these p-adic numbers. You mentioned that there are many applications in modern mathematics, but maybe you could mention one that could be helpful for the students. Or some interesting problems that can be solved in p-adic numbers that cannot be solved in other.
Yeah, for example,
systems.
maybe you, when you first learned that -1 times -1 is 1, maybe you wondered why, minus times minus is plus. But I have calculated, right? And this calculation gives you, just the evidence. Just you calculate, then you get it is 1. So I think this is a very good application of this p-adic numbers in this way. So don't you think so? I don't know. Maybe you teach this to your brother or sister. Yeah.
Maybe some other application apart from that one.
Mm-hmm.
Okay, well, I don't see anybody raising hands. So let's thank Professor Kato again for a wonderful lecture. Thank you.
Thank you very much. Thank you so much.
By the way, when you look at rational numbers, often you have that the fractional